Well, hello everyone. Let's get started with today's chemistry lesson on ionization and ionization energies. That can be found in your study guide, lesson 16. So if you'll get that out, let's get started. All right, you should be now turned to lesson 16, ionization energy. All right, to get us started, let's define what ionization is in the first place. So you should recognize this diagram in front of you. No, it's not in your notes, but this diagram you have seen before. And it depicts the Bohr model, specifically showing the electron transitions that occur when an electron gains or absorbs enough quantized energy to transition it from one energy level to the next. Okay. Now, sometimes an electron can absorb a whole bunch of energy, and that energy actually removes the electron entirely from the atom. Okay, ejects it. Bye-bye, adios. Okay, if it absorbs enough energy to do that, to eject that electron from the atom, that is known as ionization. Okay, so this electron here, again, if it's absorbing enough energy, it can be excited to a level that is infinite, meaning that it's being kicked off of the atom and ejected from it permanently. Okay, so anytime we're talking about ionization, that's what we're really referring to, is the removal or an ejection of an electron from an atom. All right, now, if you're an atom that has many electrons, you could go through many different ionization processes. For example, if you're hydrogen, because you only have one electron, you can only go through one ionization process. But say if you're lithium having 3 electrons, it can potentially go through 3 ionizations. It can lose 3 electrons, so it goes through a period of 3 times in which it would eject or ionize its electrons. Oxygen has 8 electrons, and as a result, it can go through 8 ionizations, losing all 8 electrons. And so let's take, for instance, lithium. It can lose those 3 electrons, go through 3 ionizations. So the first electron removed is always referred to as the first ionization process. Makes sense. If I remove a second electron, that's the second ionization. If I remove the third electron, that's the third ionization, and so forth until all the electrons have been removed. All right? So what I'm going to do is draw an equation for the first ionization process for a generic atom. So let's use the symbol, let's say M. And the reason why I'm going to use M, because we're going to make it stand for any generic metal. And I choose the metals because, as you're going to see soon, it's usually the metals that naturally ionize their electrons. But that doesn't mean non-metals can't ionize, okay? Any element can ionize their electrons, okay, given enough energy. All right, so let's say we have a metal, and in order to ionize an electron, it must be in the gas state, okay? And so then we're going to draw an arrow. This arrow represents that a process is going to occur. And in this case, it's going to undergo ionization. And therefore, the metal loses an electron, becoming a positive charged atom, a cation. Should make sense. It loses an electron, it's got to become an ion. It's going to be in the gas state still, and it loses that electron. We indicate that by the electron symbol, like so. So this is a generic equation for some metal losing an electron for its first ionization. If I wanted to use a real case study, let's let's use magnesium. It's a metal. It has to be in that gas state, right? And it undergoes the process, that's the arrow, of ionization, and it loses one electron, so it becomes positively charged, or positively one charged, right? Still going to be in this gas state, and then we show the electron that is being emitted or ejected in our equation, okay? So there's an example of what we would say the first ionization process, okay? What about a second ionization, though? Let's do that. So if an atom is going to go through the second ionization, it's already had to gone through a first ionization. So let's use our generic metal again in the gas state, but it's already had one ionization, so it should already be positively charged. All right, you can't do a second ionization unless the first one has already occurred. Hopefully that makes sense. It's going to go through our process of ionization, and now, because it loses a second electron, it's going to be a positive 2 charge, still in the gas state. And we're going to draw the electron that we just lost right there. All right, so this is a good example or generic example of a second ionization process and the equation for it. If I wanted to use our magnesium sample, again, it's already got to be a +1 charge in the gas state and undergoes our process of losing a second electron, making it Mg+2 in the gas state, and then the 1 electron that is being ionized or lost, okay? So there's 2 examples of the first and second ionization process. And of course, if another electron is lost, then it goes to a third ionization, which you start out with the +2 ion, right? Because it's already gone through 2 ionizations. So you start out with +2, and then you show the process of going to a +3 cation, okay? And so forth, right? All right, so where exactly are we going to start losing electrons in the first place, okay? Especially when you have multi-electron atoms, okay? Where do we begin to lose them? Well, based on Coulomb's law, if you remember, an electron that is further away from the nucleus has less energy, right? The further you go away from the nucleus, the electrons diminish in their amount of quantized energy. The ones closer to the nucleus has more energy, and being closer to the nucleus, more attraction, right? So we would assume then the easiest electrons to remove first would be the outer or valence electrons, and that is correct. So these valence electrons, one of these, is going to be removed first. So this one might be the first one, let's say, and it goes through a first ionization, and then second ionization. Let's say this is our third ionization, and then our fourth ionization. So we always remove electrons from the valence shell first, and that's critical to understand. So make sure you're good with that. And then once we've removed the outer electrons, those valence electrons, then we can work into the core electrons. So this might be our fifth ionization, and then finally our sixth ionization. All right. So essentially, we can start or we can ionize with this particular atom 6 ionization processes, starting with the valence shell first and working our way into the interior of the atom. All right, now we remember we already stated that in order to remove an electron from the atom, to inject the electron, it requires energy. Well, the energy that is needed to eject an electron or ionize an electron is known as the ionization energy. You need to become very familiar with this term. We will be talking about ionization and the ionization energy process throughout the year, okay? By definition, this is a good definition for AP and IB, is that it is the energy required to remove 1 mole of electrons from 1 mole of atoms in the gas state, okay? So these atoms have to be in the gas state in order to remove the electron in the first place. And so we're talking about the energy required to remove molar amounts of electrons from these atoms, okay? Removing 1 electron from 1 atom, the ionization energy is super, super small. So we don't really focus on that. We focus on larger quantity of emission of atoms, okay, or electrons from atoms, okay? So there's our definition of ionization energy. Now let's get into what we call successive ionizations. Essentially, a successive ionizations means that we're going to lose 1 electron after another, after another, after another, successively, starting with the valence shell first, and then working our way into the interior until all of the electrons have been removed from that atom. And that's successive ionization, all right? Now, what's cool about successive ionization is that it gives us direct evidence for the existence of quantum energy shells or energy levels, okay? And so what we're going to do is we're going to look at the data here and kind of see this evidence and where it lies. And you need to be able to point out the evidence of showing how successive ionizations does give evidence to electron shells or energy levels, okay? So to do that, I have a graph here of aluminum, and it shows the successive ionizations for the aluminum atom. Now, aluminum has how many electrons total? Okay, how many electrons total? Well, if you look at your periodic table, I'm glancing over there now, there are 13 electrons. All right, so that means aluminum has the potential of losing all 13 electrons given enough energy. And so we're going to map out the successive ionization for all 13 electrons for aluminum in this graph. So on the bottom, the x-axis shows the ionization number, and on the y-axis is the ionization energy. That would be the energy needed to remove 1 electron at a time, okay? So if you look at our graph here, the first ionization, which represents this point here on the graph, notice that it requires very little energy whatsoever, okay? It almost looks zero. It's not really zero. If I was to zoom in a little bit closer, I could tell that it definitely requires energy to remove this electron, all right? But as you notice, a gradual trend is that as we go to the next ionization, it requires just a little bit more energy to remove the electron. Oops, lights went off. If I go to the next electron, even more energy is required to remove that electron, okay? So what we're seeing is that as we're going from 1 ionization, there's ionization 6, there's this gradual increase in energy needed to remove an electron, okay? Now, let's talk a little bit why that might be. Well, first of all, where are we losing our first electrons for aluminum? Well, let's draw a simple electron structure. Well, we won't use electron configurations, but let's draw a simple structure for aluminum. Now, aluminum's going to have 3 electron shells with electrons in it. In the first shell, it's going to have 2 electrons, and then 8 electrons, and then 3 electrons. okay? So this is essentially the electron structure for aluminum. So where are we going to emit or lose the first electrons is right here on the valence shell, right? These first 3 electrons. And that is what's represented here. Let me erase these circles here. So that's what's represented here is, oops, let me do this one too, is these first 3 electrons are from the valence shell, the electrons that are furthest from the nucleus. So if they're furthest from the nucleus, they have less, they have essentially more energy, right? So what it requires is less energy to actually remove them. The nucleus does not have a strong attraction for these 3 electrons as it does for the other ones, okay? Because they're further from the nucleus. And basically, again, using Coulomb's law, we know that the distance that an electron is from the nucleus, the less attractive force it will have, or the less electrostatic force that will occur. So obviously, these are the easiest ones to remove and takes the less amount of energy. But then you'll notice there's a point here where there's an increase. Interesting. You know, there's just this little gradual change in energy, and then there's kind of this little spike here, okay? Interesting. Let's come back to that spike. Well, by the time we get to the 4th ionization, and then the other successive ionizations, these 8 electrons are found where? They're found on the next shell, right? The second shell. And so these 8 electrons are removed from the second shell. And then we have another large gap, and this is really a large jump in energy, okay? And then we have these 2 electrons that need to be removed. Where are they being removed from? It's from the first shell. These are the ones that are closest to the nucleus. These are the electrons that the nucleus has the strongest attraction for, and therefore the hardest to remove. It's going to take a lot of energy to get these 2 electrons off of the atom, much more energy than what these first 3 are required. So what do you think these jumps in energy indicate? Well, they indicate, if you guess right, they indicate from the movement from one shell to the next. And this is where that direct evidence of successive ionizations give us of energy shells. We're essentially looking at the 3rd shell right here, and then the movement to the 2nd shell. And then finally, let's do this to the 1st shell right here. So this is the 1st shell electrons, 2nd shell electrons, and 3rd. And the energy big jumps here and here is the change in energy levels. But the gaps are interesting too. All right, why is the gap so much bigger between the second and the second and 1st shell than between the 3rd and the 2nd shell? What's the difference here? Well, remember that we understand, or should understand, that there's a distance between the energy levels, right? And the 1st and the 2nd energy level distance is much greater. There's a big gap, and the gap between the 2nd and 3rd energy level is smaller. So the energy jump is going to be smaller between the 3rd and the 2nd energy level than it is between the 2nd and 1st energy level, because of the spacing between energy levels. And that should make sense. 1st and 2nd energy level, and then 2nd and 3rd energy level, right? The spacing is getting smaller here as we go away from the nucleus, right? So this is pretty good, I think, evidence to really give us a clue that we're on the right track, that energy levels are there. They have that existence, okay? Of course, we know it's a little bit more complex with the quantum model where we have subshells, but this does give us that some thinking there of that evidence. All right, what I want you to do is take a moment and I want you to draw the successive ionizations for sulfur. I want you to think if you can come up with that on your own, all right? And see if you can draw that in. And then, so go ahead and pause this video for a moment and you put in what you think the successive ionization graph should look like for essentially for sulfur, okay? So pause it. We'll come right back and take a look at it. All right, so let's take a look. So we know that sulfur has how many electron shells, first of all? Well, it has 3 electron shells. So let's draw those electron shells really quick here for sulfur, all right? Now, how many electrons are in the first shell? Gonna be 2, all right? And then we have our 8 electrons here. Actually, sulfur has, 3 shells. I had to double check that. And then it has, I believe, 6 electrons, right, on the third shell, okay? So shell 1, 2, and 3, all right? So total of 16 electrons that sulfur can go through the ionization process with. So what we're going to do is I'm going to show you what I would probably do. I'm going to lose the first 6 electrons. 1, 2, 3, 4, 5, and 6. And I'm sort of gradually creating energy there. And then there's going to be a jump. Sorry about this.
Shelley Fine, Lindy McKay, Jordan Hewlett.
All right, sorry about that interruption here. So let's go back to our screen here. All right, so when we redraw this, so again, we're gonna have our 1, 2, 3, 4, 5, and 6 ionizations to start with. And then there should be a jump in energy as we go from the next energy level. And then the next 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8. And then there should be a large jump, and then the last 2 electrons there. So here's our first energy shell, our jump, our energy there, and then our big jump between the second and first, and something like that. So something like this. I know it's a crude, rough draft copy, but you get kind of the idea there on that, okay? So that is the successive ionizations for sulfur. All right. Let's actually, I'm going to do something here. Hold on. All right, I'm going to go back to my screen here. Sorry about that interruption. All right, so what we're going to do is, since we've talked about successive ionizations, we're going to turn our attention now to first ionization energies, okay? So remember that atoms that lose their very first electron goes through their first ionization. So the energy required to remove the very first electron is known as the first ionization energy, okay, for that element. Now, if an atom loses a second electron, that energy required to remove the second one is known as the second ionization energies. And then you have the third ionization energy for removing the third one, and so forth and so forth. So what we're going to do is take a moment to look at some data for the first ionization energies, the energy required to remove the first electron for the first 36 atoms on the periodic table. All right. Now, this data is actually quite interesting when you look at it on a graph. And you can learn a lot about the structure of the atom from the ionization data for these first ionizations. And what you need to walk away with is looking at this data with showing that it gives us some great evidence of the existence of not only energy levels or energy shells, but also the subshells, the S subshell, P subshells, and D subshells, okay, as we'll see in a moment here, okay? So we'll start out with the basics, and then we'll kind of dive into the more specifics on subshells and so forth. All right, so on the x-axis is the atomic number for the element that we're looking at. And then on the y-axis is the ionization energy, the first ionization energies, okay, for each of these 36 elements that we're looking at here. So each data point represents an element and its first ionization energy. So if I was to do this, this would be hydrogen then. This would be the first atom on the periodic table with an atomic number of 1. And then this would be helium. And then we have what? Lithium right here. And then we have beryllium. And then we have what? This is boron. And then this is carbon, nitrogen, oxygen, fluorine. And then this top one here is going to be neon. Okay. And then we start again using the, this one right here is what? Sodium, and then so forth, magnesium. Okay. So first of all, I want you to look what's happening to the first ionization energies as we go from hydrogen to helium, okay? Well, there's an increase, right? It's easier to remove the first electron from hydrogen than there is from helium, okay? So there's this increase here. Now, notice that on the periodic table, hydrogen and then helium, that's in one period, right? In fact, that's the first period. Well, let's look at lithium to neon. What's generally occurring here across this period, okay? As we go from lithium to neon, we see a general increase in the first ionization, generally. There's a few low points. This low point between nitrogen and oxygen in beryllium and boron. And we're going to come back and we're going to address those low points. But for the most part, there's a increase in the first ionization energy. So what we're saying is it's easier to remove the first electron from lithium than it is from neon, okay? And across that period, it's getting harder. As you go across period 2, it's getting harder and harder to remove the first electron, okay? Well, what about this group of elements down here? Well, that's period 3, right? Right here. This is period 3, okay? And you see pretty much the same general pattern that as we're going across, for the most part, it's getting harder and harder to remove the first electron. It's taking more and more energy to do so, okay? So it appears that there is a trend that's occurring as going across a period left to right. And that is it's taking more and more energy to remove the first electron, and it's getting harder and harder to remove the first electron as we go left to right across the periodic table. So why is it getting harder and harder to remove an electron? Why is that energy increasing? Well, it goes back to Coulomb's law and to effective nuclear charge. Just like atomic radii, as we're going across the periodic table, a period, left to right, the atom's size is decreasing, okay? And why is it decreasing? Because we're adding more protons to the nucleus, and the effective nuclear charge is increasing, all right? So if we're adding more protons to the nucleus, and the effective nuclear charge therefore results in an increase, there's going to be a stronger electrostatic force attraction on the valence shell. And remember, we're going to remove the valence electrons first. So not only will that shrink the atom, making it smaller by adding more protons to the nucleus, but it also creates a stronger attraction and harder to remove an electron. So the smaller the atom, the harder to remove the valence electrons, okay, as well as really it's the number of protons in the nucleus. So we can say that going from left to right across a period in the periodic table, there's an increase in ionization energy because there's an increase in proton number in the nucleuses of those atoms. As a result, there's an increase in the effective nuclear charge, creating a stronger attractive force. And we see that all the way through the periodic table. The first period, second period, fourth, and so forth. Okay. All right. So there's a general trend across a specific period in the periodic table for first ionization. All right. What about going down a group? Okay. What do we kind of see happening as we move down one particular group or another? Okay. Well, if you look at this from lithium or from hydrogen to, and actually maybe it'd be better to look at this one because it's blown the scale a little bit better. So helium, neon, this one is argon at this point, argon. And then after argon, this is krypton right here. Oh, sorry, actually, it's not krypton. My bad. Jumped ahead of myself. This is krypton. Okay, what are we kind of seeing here? We're kind of seeing a decrease, okay? And that's kind of what's happening. As you go down a group, there's going to be a decrease in the first ionization energy, all right? Why is there a decrease in ionization energy as we go from top to bottom? Okay, a decrease from top to bottom. In other words, an increase would occur going from bottom to top, okay? So why is there that decrease? Well, what are we doing? Going back to Coulomb's law, we are adding more electron shells as we go down. Remember that by adding more electron shells, not only is the valence shell getting further from the nucleus, but the atom is getting larger, okay? And so as the valence shell is getting further away, and we're removing the electron, that first electron from the valence shell, if it's getting further away, there's going to be a less of attraction on the nucleus from that valence electron. So that valence electron is getting easier to remove because it's getting further away from the nucleus. Coulomb's law, right? Distance has a big impact on the attraction, the electrostatic attraction between the protons and the electrons in the valence shell, okay? So when we look at the periodic table, we're going to see two major trends, okay? Two big trends. Number one, going across the periodic table. In fact, when we do this, I'll come back to this table in just a minute and look at atomic structure. But let's write this down so you can kind of get the trends down. All right. So the ionization trend across a period. The ionization energy gets larger as you move across the periodic table left to right. Why is this? Okay, and that is because there's an increase in the nuclear charge due to the increase in number of protons. Okay, so that's the general trend across a period that you need to be very comfortable with first ionization energies. Okay, so what's again the trend as we go from top to bottom? So as we go down the periodic table, the trend shows that there is a decrease in first ionization energies, a decrease. Why? Because we're adding a new valence shell every time we go down from one element to the next. Therefore, this increases the distance that the valence electrons are from the nucleus. And again, using Coulomb's law, the electron, as it gets further from the nucleus, the attractive force, the electrostatic force of attraction, gets weaker and weaker and weaker, okay? And therefore, it's easier to remove that electron from the valence shell, all right? So those are the two major periodic trends for ionization that you should be clear on, okay? So for example, let's look at potassium versus, say, rubidium, okay? So potassium is above rubidium. And which one of these elements would have a first larger ionization energy? If you said potassium, you would be correct. The ionization energy should get bigger, IE for ionization energy. The ionization energy should increase going up. And that is because potassium has one less electron shell than rubidium. Rubidium's valence shell is much further away from the nucleus than potassium's, okay? So potassium, it would be harder to remove the first electron than from rubidium, okay? That's just kind of an example there. All right, let's go back to our graph and start finishing up here with looking at atomic structure and how this gives us some evidence, okay? Well, just like we saw with successive ionization energies, the first ionization energies also give us evidence of electron shells. So if you think about this, this is period 1, and this is period 2, and then what we see is these drops in energy between period 1 and period 2. Period 3, we also see a gap here, a drop, okay? Now, why are these drops there? Well, it's because we're moving from one electron shell to the next. Essentially, this is representing the electrons that are the closest to the nucleus, or the first electron shell. And this would be representing second electron shell in the third electron shell. So these gaps in energy, these big drops in energy, is because we're moving from one shell to the next to the next, okay? If we were not moving from one quantized energy level to the next, then we would not see those drops, okay? These drops would not be here. These points that we're looking at here would not exist, because the electron would have a gradual change, because it would be anywhere with wherever it wanted in the atom. But because it's defined to specific regions in the atom, you're going to have those spaces where the electron cannot be in. So therefore, you do have these energy levels, okay? So I need you to understand that these drops in energy that we're seeing here is a direct result of moving from one electron shell to the next, okay? Hopefully you see that. That's important. Okay, now I told you that we were going to come back and look at these weird outliers here where this is beryllium. So we draw beryllium again, and this is boron, and right here this is nitrogen, and this is oxygen. So from beryllium to boron, we see a drop, and then from nitrogen to oxygen, we see a drop. Why the heck do those drops occur? Why are these outliers in the data occurring? Okay, they're important. We got to look at these outliers. So let me do this. I'm going to go forward a little bit here, and I'm going to draw a diagram to show you what's going on with those drops. So let's look at the drop between beryllium. Okay, that drop between cannot draw. Okay, so from beryllium, Be, that drop to boron, okay, first, and then we'll do the other one. So to understand this, we need to look at the electron configuration of beryllium and boron, okay? So I'm going to do that by showing a more or less an orbital diagram. So we have the 1s. We're going to do boron first. So we have the 1s for boron, and it's going to have 2 electrons in it. And then I have the 2s, which also has 2 electrons in it. Arrows going in opposite directions. They have opposite spins, all right? So this is the electron configuration essentially for boron, or the orbital diagrams. So the 1s2 and 2s2. Okay. Now let's look at, oh, sorry, not boron, beryllium. So sorry, beryllium. Now boron, let's look at boron, okay? It also has a 1s, of course, with 2 electrons in it. It has a 2s with 2 electrons in it. But then it's also going to have 1 electron in the 2p, okay, right? That should be boron structure. So it should have 1s2, a 2s2, and a 2p1, okay? Now, why do we see that drop from beryllium to boron? Well, we know that the outer electron shell for beryllium is the 2s, right? This is the valence shell. So the first electron that's being removed from beryllium is coming from the 2s. All right. Now, what about boron? Well, this is the valence shell, the 2s and the 2p, right? This is the valence shell. Well, which electron out of these 3 electrons is most likely to be removed first? Are removing the 2p or the 2s first? Well, you know that based on this energy diagram, the 2p, even though they're on the same energy level, the 2p subshell has more energy than the 2s. So therefore, we're going to lose the electrons in the 2p before the 2s, okay? So this electron is much easier to remove than the ones from the 2s, hence the drop in energy. We have no electron in the 2p for beryllium. And since beryllium's 2s sublevel is essentially lower in energy, so, or has essentially a stronger pull to the nucleus than the 2p, this electron is going to be easier to remove because it already has a high enough energy. Just need to add a little bit more and boom, eject it. Okay? So this right here is an important, vital example of why we're dropping from beryllium to boron in those kind of oddities there, the anomalies in the data. But this also gives us direct evidence that there are subshells that exist, because it shows us a clear definition, or that there is a 2s subshell and a 2p subshell within the same electron shell. Okay? The difference between these two subshells is really their energies, not their distances, but their energies. The 2p and the 2s being in the same subshell area, they have different energies only. Okay? So that's important to note. Okay. So now let's look at the other one. That's the nitrogen to oxygen decrease. Okay. So again, we're going to look at nitrogen, the electron structure. So nitrogen has a 1s subshell with 2 electrons in it. It has the 2s subshell with 2 electrons in it. But then it has electrons in the 2p. Now, we're going to follow Hund's rule, right? It has 3 more electrons that we need to fit in this. And so, following Hund's rule, we're going to put 1 electron into each one of those p orbitals, okay? So we have 3 half-filled p orbitals in the 2p subshell, okay? Now, let's look at oxygen. Oxygen also has a 1s subshell that is full. We have a 2s subshell that is full. And then it has its 2p subshell. And following Hund's rule, it has 1 electron, another electron, and another electron. However, oxygen has 1 more additional electron than nitrogen, and it's going to have to occupy an already orbital that has an electron in it, okay? So with oxygen, we have 2 half-filled p orbitals and then 1 full-filled p orbital, okay? So what accounts for the difference in energy? Why does it easier to remove the first electron from oxygen than nitrogen? Well, where are we removing the first electrons for nitrogen is right here, the 2p, right? We have the valence electrons in the 2s and the 2p, but we already talked about that we're going to lose electrons from the 2p before we do the 2s, okay? So one of these 3 electrons will be lost first. Well, what about for oxygen? Well, again, we're going to start with the 2p, but where in the 2p? We're going to look at this electron, or this electron, or this one, or this one. Well, we're actually going to lose this one, okay? It goes along with Hund's rule, and it goes along with the fact that these 2 electrons occupying the same space, because they're both negative electrons, negative and negative, even though they have opposite spins, they are negative and negative particles. They don't like each other at all, and they're going to want to separate. All right. Remember, Hund's rule is that it's more stable to put electrons in each of the 2p orbitals first, half-filled, because we don't have the electron-electron repulsion going on. All right, so this electron right here is the one that's not stable compared to the other 3. So it is this electron that is going to be way easy to remove compared to the other ones that we see in the 2p. So because we have since we have a 2p orbital for oxygen that is full, this electron that has the opposite spin is going to be the one that's going to be really destabilized because of electron-electron repulsion, electron-electron repulsion. And therefore, this will be easier to remove, okay? And that's why we see the drop in energy. Again, this gives us evidence of subshells, but it also gives us evidence of Hund's rule, and it gives us evidence that we have 2 electrons per orbital with opposite spins. It gives us a lot of evidence that we're seeking for to give us reassurance on atomic orbitals and subshells and so forth, okay? So all of this ionization evidence is critical for the AP and IB exams. So please study it well. The AP and IB people who make the test, they love ionization energies. Therefore, on my test, I will test you on this as well in a great amount, okay? A several number of questions, okay? So study, come to class with questions if you have some, and we'll have a discussion on it, okay? So that is it for ionization and for this lesson. So we will sign off for now and see you next time.